Artificial general intelligence may redefine intelligence itself, but quantum computing threatens to redefine reality at its most fundamental computational level. We are entering a period where the basic rules that governed classical computers for 80 years are being challenged by machines that operate according to the principles of quantum mechanics. This is not an incremental upgrade. It is a paradigm shift rooted in the physics that governs atoms, photons, and subatomic particles. Governments in the United States and Canada are investing billions into this technology, not as a speculative gamble, but because the implications touch cybersecurity, national defense, pharmaceuticals, artificial intelligence, financial systems, and the architecture of the Internet itself. At the center of this transformation lies a simple but unsettling possibility. The day encryption as we know it collapses. To understand why quantum computing is so disruptive, we must begin with classical computation. Every laptop, smartphone, data center, and satellite system today operates on bits. A classical bit exists in one of two states, 0 or 1. All modern digital infrastructure from banking authentication to encrypted messaging rests upon this binary abstraction. Classical processors perform operations by manipulating billions of these bits in precise electrical sequences. For decades, transistor miniaturization followed Moore's law, doubling computational density roughly every 2 years. But as transistor scales approach atomic dimensions, quantum effects begin to interfere. Ironically, the very physics that once threatened classical scaling now provides the foundation for the next computing revolution. Quantum computing replaces classical bits with quantum bits, or qubits. A qubit does not merely represent 0 or 1. It can exist in a state known as superposition, where it effectively embodies both possibilities simultaneously until measured. This is not metaphorical. It is a measurable physical phenomenon verified in countless experiments in quantum mechanics. In classical logic, a system evaluates one configuration at a time. In quantum logic, a system can encode a probability distribution across multiple computational paths at once. As more qubits are entangled together, the system's representational capacity grows exponentially. 2 classical bits encode 4 states one at a time. 2 entangled qubits encode 4 states simultaneously. 30 entangled qubits represent over 1 billion states in parallel. This scaling behavior is what makes quantum computing fundamentally different rather than merely faster. However, superposition alone is not sufficient to produce computational advantage. The second principal, entanglement, is where quantum computing becomes extraordinary. Entanglement links qubits such that the state of one cannot be described independently of another, even if separated by distance. Einstein famously referred to this as spooky action at a distance, but decades of experimental validation have confirmed it as a real physical property. In computational terms, entanglement allows quantum systems to encode correlations that classical systems cannot efficiently replicate. It creates a multidimensional computational space where operations manipulate probability amplitudes rather than deterministic states. Algorithms operating within this space can exploit interference patterns to amplify correct solutions and suppress incorrect ones. The practical obstacle has always been decoherence. Quantum states are fragile. Any interaction with the external environment, thermal fluctuations, electromagnetic noise, stray photons can collapse superposition and destroy entanglement. This collapse forces qubits into classical states, eliminating the quantum advantage. Maintaining coherence long enough to perform meaningful computation requires extreme engineering precision. Many quantum processors operate at temperatures near absolute zero to reduce environmental interference. Others use trapped ions suspended in electromagnetic fields. Still others experiment with photonic systems that manipulate light particles. The race is not simply about increasing qubit count. It is about increasing qubit stability and reducing error rates. Error correction in quantum systems is itself a complex challenge. Classical error correction duplicates bits and checks parity. Quantum error correction must preserve superposition while detecting faults, which cannot be measured directly without collapsing the state. This requires encoding logical qubits across multiple physical qubits in entangled structures that can tolerate disturbances. The engineering difficulty is immense, but progress has accelerated. Laboratories in North America and Europe have demonstrated logical qubits with error rates decreasing year over year. As coherence times increase and gate fidelities improve, the threshold for practical quantum advantage draws closer. The turning point for public awareness came when researchers demonstrated that certain computational tasks could be executed by quantum processors faster than by the most powerful classical supercomputers. Although these tasks were highly specialized and not directly applicable to everyday problems, they represented proof of principle. The broader impact becomes clear when we examine cryptography. Modern encryption systems such as RSA rely on the mathematical difficulty of factoring large integers into prime components. Classical computers would require astronomical time to factor sufficiently large keys. This computational hardness secures global banking, military communications, cryptocurrency wallets, and secure internet browsing. In the 1990s, mathematician Peter Shor developed a quantum algorithm that changes everything. Shor's algorithm demonstrates that a sufficiently powerful quantum computer can factor large integers exponentially faster than classical algorithms. In practical terms, this means that once quantum hardware reaches a certain scale and reliability threshold, widely used encryption systems could be broken. The phrase "the day encryption dies" is not hyperbole. It is a technical prediction based on algorithmic mathematics. The risk is not limited to future communications. Adversaries could capture encrypted data today and store it until quantum systems become powerful enough to decrypt it later. This harvest now, decrypt later strategy is already influencing cybersecurity planning. Cryptocurrency communities are particularly attentive to this threat. Bitcoin relies on elliptic curve cryptography for wallet security and transaction verification. While the blockchain itself is resilient due to distributed consensus mechanisms, individual private keys could theoretically be derived using large-scale quantum computation. The scenario when quantum computers break Bitcoin depends on whether quantum hardware surpasses specific cryptographic thresholds. Most experts estimate this would require millions of stable, error-corrected qubits far beyond current prototypes. Yet the pace of investment suggests that post-quantum cryptography is no longer optional. Governments and standards organizations are developing quantum-resistant algorithms designed to withstand attacks even from advanced quantum machines. The shift toward post-quantum cryptography is already underway. In the United States, federal agencies are transitioning to encryption standards believed to be resistant to quantum attacks. Canada has invested heavily in quantum research institutions and startups focusing on secure communications. The economic stakes are enormous. Nations that lead in quantum computing could gain intelligence advantages, industrial optimization capabilities, and pharmaceutical breakthroughs. The race is technological but also geopolitical. Quantum supremacy in cryptanalysis could alter global power balances as dramatically as nuclear technology once did. Beyond cryptography, quantum computing promises transformative applications in materials science and chemistry. Many molecular interactions are governed by quantum mechanical behavior that classical simulations approximate only crudely. Quantum processors can, in principle, simulate quantum systems directly. This opens pathways for designing new drugs, optimizing battery materials, developing high-temperature superconductors, and accelerating carbon capture technologies. The pharmaceutical industry, which spends billions on trial-and-error molecular modeling, could reduce discovery timelines dramatically with accurate quantum simulations. Artificial intelligence may also intersect with quantum computing. Machine learning models often require enormous computational resources for optimization. Quantum-enhanced optimization algorithms could, theoretically, explore solution spaces more efficiently for certain classes of problems. However, this remains an active research area rather than an established advantage. The interaction between quantum computing and AI may ultimately yield hybrid architectures, where classical and quantum processors cooperate, each handling domains where they are strongest. The concept of a quantum internet extends these ideas beyond isolated processors. A quantum internet would use entangled particles to transmit information with theoretically unbreakable security. Quantum key distribution allows two parties to detect eavesdropping, because any interception disturbs the quantum state. Experimental quantum networks have already demonstrated entanglement across metropolitan distances. Scaling this to global networks would require satellite-based quantum repeaters and advanced photonic engineering. If realized, the quantum internet could redefine secure communications for governments and financial institutions. Yet immense engineering barriers remain. Scaling qubit counts without increasing noise is difficult. Fabrication consistency at atomic precision is challenging. Cooling systems are energy-intensive. Error correction overhead remains high. The optimistic narrative envisions exponential growth in capability. The cautious perspective emphasizes the unpredictability of physical constraints. Unlike classical transistor scaling, quantum scaling does not follow a simple empirical law. Progress depends on breakthroughs in materials science, cryogenics, and quantum control theory. Public discourse often oscillates between exaggerated hype and dismissive skepticism. The realistic assessment lies between these extremes. Quantum computing will not replace classical computing for everyday tasks, such as browsing or word processing. Its strength lies in solving specific classes of computationally intractable problems. It is a specialized instrument, analogous to a particle accelerator rather than a personal computer. The transformative impact arises from targeted applications in encryption, optimization, and simulation. The psychological dimension of the day encryption dies captures public imagination, because encryption underpins digital trust. If financial systems were suddenly vulnerable, economic stability could be threatened. In practice, the transition will likely be gradual. Cryptographic systems can be upgraded before quantum hardware reaches destructive capacity. International collaboration may mitigate unilateral exploitation. However, the mere possibility of cryptographic vulnerability introduces strategic uncertainty. Quantum computing also forces a philosophical reflection on computation itself. Classical computing assumes determinism at the logical level. Quantum computing embraces probabilistic amplitude manipulation. Results emerge from interference patterns rather than step-by-step deterministic evaluation. This challenges intuitive notions of problem solving. Engineers must think in terms of amplitude, amplification, and constructive interference rather than linear logical operations. Education systems are adapting. Universities are expanding quantum information science programs. Interdisciplinary training now combines physics, computer science, electrical engineering, and mathematics. The workforce pipeline must expand if national strategies are to succeed. Investment is not solely in hardware. It is in human capital capable of operating at the frontier of quantum mechanics and algorithm design. Canada's quantum ecosystem has become globally competitive, with research clusters focused on photonic quantum processors and secure communications. The United States has launched coordinated national initiatives integrating academia, private industry, and federal laboratories. Venture capital funding has surged. Startups are exploring alternative qubit implementations including topological qubits, which theoretically offer greater error resistance. Whether any single approach dominates remains uncertain. As breakthroughs in qubit stability accumulate, attention shifts toward scaling architectures. Demonstrating 50 or 100 coherent qubits is scientifically impressive. Demonstrating thousands with low error rates moves toward practical impact. The threshold for breaking widely used encryption schemes may require millions of logical qubits. Achieving that scale demands engineering precision at unprecedented levels. The quantum internet concept adds further complexity. Entanglement distribution across large distances requires quantum repeaters that preserve coherence. Satellite experiments have shown entangled photons transmitted between ground stations. These demonstrations, though limited, prove feasibility. A global quantum communication network would fundamentally alter secure diplomatic and military channels. Critics argue that quantum computing timelines are overly optimistic. Engineering challenges may slow progress for decades. Others argue that exponential technological acceleration could surprise skeptics. Both positions acknowledge uncertainty. What is indisputable is the strategic importance assigned by governments and corporations. Funding patterns signal belief in eventual viability. The most dramatic scenario remains the intersection of Shor's algorithm and large-scale fault-tolerant quantum machines. In that scenario, RSA and similar encryption schemes become obsolete overnight. Financial institutions, intelligence agencies, and digital platforms must therefore prepare proactively. Post-quantum, cryptographic standards aim to replace vulnerable systems before crisis emerges. This transition resembles upgrading the foundation of the Internet while it remains operational, a delicate and complex task. The narrative of quantum computing as a thriller emerges from this tension between extraordinary promise and existential risk. It is a story where physics meets geopolitics, where subatomic behavior influences global security, where microscopic coherence times determine macroscopic economic stability. The science is rigorous, experimentally validated, and progressing steadily. The implications are systemic. Quantum computing does not merely promise faster calculations. It redefines the computational substrate upon which digital civilization operates. Superposition expands representational capacity beyond binary constraints. Entanglement creates correlations impossible in classical systems. Decoherence reminds us of fragility at the quantum scale. Shor's algorithm demonstrates that mathematics itself changes meaning when executed on a different physical platform. The day encryption dies may never arrive as a sudden catastrophe. Instead, it may appear as a controlled transition, a quiet migration to quantum-resistant standards, or it may arrive unexpectedly, triggered by an unforeseen breakthrough in qubit stability. The outcome depends on engineering progress, regulatory foresight, and international cooperation. What remains certain is that quantum computing is no longer theoretical speculation. It is an active field reshaping cybersecurity strategies, national investments, and scientific research priorities. As coherence improves and qubit counts rise, the boundary between laboratory demonstration and industrial application narrows. In that narrowing gap lies one of the most consequential technological shifts of the 21st century. The quantum revolution is not about replacing classical computers in your home. It is about transforming the invisible infrastructure that secures data, models molecules, and underwrites economic trust. When viewed through that lens, quantum computing and the quantum internet are not merely trending topics. They are foundational technologies in formation, poised to redefine digital civilization at its core.